Last lesson gave us entropy, the average surprise when outcomes come from P, and the exact number of bits the best possible code needs. But all of that assumed you knew P. In practice, you almost never do. What you have is a model, Q, an estimate, a network's output, an educated guess. So the real question is, what it costs you to use Q, while reality goes on running on P. Cross-entropy answers exactly that. H of P, Q equals minus the sum over X of P of X times log Q of X. The same shape as entropy, with one crucial swap. The weights come from P, but the logarithms come from Q. The coding picture makes it concrete. Build the optimal code for Q. That assigns an outcome X, a code word of length, minus log Q of X bits, short codes for whatever Q thinks is likely. But the symbols actually arriving are drawn from P. So the average length you pay is the Q length, minus log Q of X, averaged against the P frequencies. That average is the cross-entropy, E under P, of minus log Q of X. Now the central fact. Cross-entropy is never smaller than entropy. H of P, Q is at least H of P, with equality if and only if Q equals P. That is Gibbs, inequality. Make it concrete with a coin that lands heads 70% of the time. Its entropy is about 0.88 bits, and no code can beat that. Model the coin correctly, and you pay exactly 0.88. Model it as a fair coin, and you pay a full bit instead. The gap is pure waste, bought by believing the wrong distribution. Push Q further from P, and the penalty grows without any limit. As Q of X approaches 0, on an outcome that P still produces, minus log Q of X blows up. And notice it is not symmetric. H of P, Q and H of Q, P are different numbers. The order matters. You have almost certainly optimized this already. In classification, the true label is a one-hot distribution P, with all its mass on the correct class. Every other term in the sum is multiplied by 0, so the whole thing collapses to one term, minus log Q of the correct class. That is the cross-entropy loss, the standard objective for training a classifier. Every time you minimize it, you are pushing Q toward P in precisely the sense this lesson defines. And it is an old friend in disguise. Minimizing cross-entropy over a family of models is identical to maximizing likelihood. The cross-entropy loss is just the negative log likelihood averaged over your data. That is Lesson 22's maximum likelihood estimation, arrived at from the coding side. Cross-entropy, H of P, Q, is minus the sum of P log Q, what you pay per symbol when the world runs on P, but your code was built for Q. It is bounded below by the entropy of P, with equality only when Q equals P, and it is asymmetric. Minimizing it is maximum likelihood wearing a different hat. Next, subtract the floor. That excess H of P, Q, minus H of P, is the Kullback-Leibler divergence, a direct measure of how wrong Q is.